Oh, this is what I was going to ask.
Okay, so we're talking about, last time we were talking about lifting things. The time before that we were talking about universal law of gravitation. I feel like we're still sort of like in everyday mode. And as I look at this, the first thing I think of when I look at this object sliding across the ground, a 10 kilogram object, goes for 25 meters. And I don't know the size of a standard curling rink. I don't know if you guys do, but 25 meters is probably a little on the big side. Let's just pretend though that this is like a curling stone, because it's definitely bigger than a hockey puck. Okay, and it's sliding across the ground. And so let's throw in some values. 25 meters. Delta D equals 25.0 meters. Make sure you can see how thick my writing is there. And it says that we got a mass of 10.0 kilograms. And it experiences 3 newtons of force. So then it seems like as it slides, it's going to experience 3 newtons of force working against it. So I'm going to say that Fk is equal to 3.00 newtons. I actually have a little bit of a beef with this picture because it looks like it's going from point 1 to point 2. And at point 1, it looks as if there's a force acting on it. If this was a curling stone, when would that force stop? Anybody who's ever watched curling? When would that force stop? Yeah. No, the forward force doesn't stop when the stone stops. Yeah, when the person lets go of it. When the person lets go of the curling stone, that's when that applied force stops. So that's my beef with this picture. I really should scribble out or white out that initial force, because if I'm talking about the slide time for this rock, I'm talking about after release, after it gets let go of by the curler, if you know what I mean, okay? What I could say is that it has an initial velocity, perhaps, but I shouldn't attach that to my actual object. So this is me criticizing my own picture. Guys? Sorry. All right. So as I'm looking at this, displacements to the right, force due to friction would be acting on it throughout. And it looks like the question is, how much work is done by friction? Of course, work is equal to force times displacement times cosine of theta. In this case, the constant force doing the work, the friction, Fk, and we can talk absolute values if we want to, just to drive home that there's no reference frame. It's just a relative angle between the two. I haven't talked about what the theta is. But again, we discussed this yesterday. I'm going to draw these two vectors, not as a free body diagram, just so that we can see the two vectors. Fk goes this way, and delta D goes this way, which means that the angle between them is what? 180, yeah. 180 degrees. And last day we also talked about the idea of the unit curve for the cosine function, and the fact that we would have 1 minus 1 at 180 degrees for theta. Cosine ends up being minus 1, and at 360 it comes back to 1 again. At 0, obviously it's 1. So if this guy is 180 degrees, we've just introduced a factor of negative 1 into this. The fact that we're introducing a negative 1 into this means that there's going to be a negative sign out front of whatever we calculate, which means that, unsurprisingly, friction is going to do negative work, or for the purists out there, friction is going to rob energy from the system. Okay? So subbing in our values, 3.00 newtons, displacement, 25 meters. I chose nice round numbers. Everything's 3 sig figs. You know, times negative 1, sure, why not? And we get 75.0 units, not Newton meters. Joules, yeah. Now the reason I say not Newton meters is that Newton meters is actually a unit that we reserve for torque. And torque is when you think about this. If I've got a lever, this is a lever, think like a toilet flush lever. If I press down on the lever here with a force, isn't it a certain radius away from the pivot point on the toilet flush? And torque actually uses what's called a cross product, where torque, let's just make it a fancy T, is equal to force times radius times sine of the angle between those two values. And of course, forget about the sine or what a cross product really is. Let's just look at the units. the units for torque would then be newtons times meters, right? And so for energy, we call them joules. We don't call them newton meters because we reserve newton meters for torque, because the units will work out to be the same thing, even though obviously if you know anything about twisting stuff, a twist is a thing which should be described mathematically, absolutely. And energy is a thing which should be described mathematically, absolutely. And they're not the same thing, okay? They just happen to have the same units. So we distinguish the two this way, and the only reason I'm drawing attention to that is to make sure that everybody knows we gotta call energy joules, we can't call energy newton meters. Even though, yeah, I get that it looks that way, okay? Everybody cool with that? All right, thumbs up. And we could make a little statement here that if this is a curling stone, the object loses. Oh, I didn't even put a negative sign out front. Nobody said anything. But I'm going to underline loses in red. Loses 75.0 joules of energy. So if I talk about it in terms of energy loss, I can say that it loses 75.0 joules of energy to address the negative sign. Or somebody else in another time and place might say that negative 75 joules of work is done on it. Either phrasing is totally cool. All right, so how fast is it going after traveling 25 meters? Well, let's see, maybe we need to know more information about this. And so I'm going to throw more information into this problem. I'm going to say, hey, what I didn't tell you before was that it started off going at 10 meters per second. So let's throw this in here. If the stone starts at 10.0 meters per second, so when it gets released, I suppose. And if we do that, then we say, okay, well, work is really just a way to apply a change of energy, whether you're giving energy or taking away energy. In this case, we're not giving any gravitational potential energy or taking away any gravitational potential energy because it stays at a steady height. Look, this thing slides across the same surface the whole time. So we'd say that the work is causing a change in kinetic energy. And so we could expand this out and we could say, okay, well, kinetic energy is 1/2 mv squared, but it would be 1/2 mv2 squared minus 1/2 mv1 squared. Reason we would say that is delta EK would have to be EK2 minus EK1, final minus initial. And I think I'd like to go about trying to get V2 all by itself, because I'd like to find what the final velocity is, and I'd rather not plug in my values prematurely. I'd like to be set up for the next time I have a really similar problem. So getting V2 all by itself, I'd say W, take the 1/2 mv1 squared over to the other side, plus 1/2 mv2 squared. Oh my goodness. I just said what I was doing and I didn't do it right. 1/2 mv1 squared equals 1/2 mv2 squared. We go back up to the other side here, and I have to multiply both sides by 2. So 2 times work plus 1/2 mv1 squared equals mv2 squared. Divide both sides by m. You know what, I'll just do it in red so I don't have to add an extra line here. And then what else should I do to not have to add an extra line? Square root both sides, yep. So then I end up having, look, the m's canceled out, the square root cancels out. So I end up having V2 is equal to 2 times, open bracket, the work done on the object plus 1/2 mv1 squared, close bracket, divided by mass. Notice that there's not a mass in both of those binomial terms, so I can't cancel out the mass, sadly. And I've got this nice little expression. I've run out of space in this column. Ugh, I hate when that happens. So V2 is equal to 2 times the work done, nice even 75, so negative 75.0 joules, plus 1/2, I hate this, 1/2 times, I'm gonna have to wrap around, 1/2 times the mass was 10 kilograms, times 10 meters per second squared, and then close off that bracket, all divided by 10 kilograms and square root the whole shebang. Oh my gosh, don't show a math teacher that I just did that. Okay? But we know what happened, right? Like this isn't like unreadable. And we plug the number in. Now sadly, because it's a square root, it's going to be a plus or minus. But doesn't it make sense that we really only care about the magnitude anyway? So what's the V2 going to end up being for this thing? Starts off at 10 meters per second. How fast is it going when it gets to the end of 25 meters? Yeah. I got 5.916. Does anybody want to second that motion? Motion seconds. Anybody else second it? Reed says yes. Meters per second. Rounded off to 3 sig figs, which we started with. So approximately 5.92 meters per second. Nice. Okay, so it's slowed down. Slowed down a fair bit. If you're a curler, it's good that it didn't come to a stop, because if this was a 25-meter long run, you'd want to have it still having speed when it hits the rocks at the other end, right? Unless there's no other rocks on the ice, in which case it probably just went through the house. And if you're not a curler, that maybe doesn't mean a lot, but oh well. Anyway, how many people are curlers in the room? Yeah, me neither. It's okay. I did it in university just for fun. It was like a Friday night thing. We get together after a physics tutorial, and we go out and we go curling. It was a league. I can't remember what our name was. We had some name that was a ridiculous pun or something. Anyway, I think that was the rule of the league. You had to have a pun for a name. All right, so example 2. What if I told some kinematics, if I'm told some kinematics or dynamics observations about a scenario? Let's just see what happens if we're told some stuff. Well, we don't know what the mass of the object is, but we know that it has an acceleration of 4.0 meters per second squared. And just like the previous problem, it travels 25.0 meters. Let's just say that its acceleration, unlike the curling stone, is towards the right, and it also travels towards the right. So this thing is accelerating in the direction in which it's traveling. In other words, the net force must be along with its motion. It's picking up speed. It's some sort of like a rocket skateboard or something like that. Who knows, okay? Say, okay, well, it starts from rest. If it starts from rest, 0 meters per second, we've got a question. Find the work done if the motion was achieved by a 10 Newton force to the right. All right, well, if this was something like a rocket skateboard, we could say, okay, well, the work done by applied force is going to be force applied times absolute value times delta D times cosine theta. I have no diagram, but I do know some direction just based on the givens. So I got to be able to interpret information from writing, which means that cosine of theta is going to be 1 because theta must be equal to 0 degrees based on the information that we have there. This is just reading between the lines on the information rather than looking at a picture per se. And so we sub in our values. F applied is going to be 10 newtons. Oh, we should have put that in because we just got given that information. 10.0 newtons times delta D, 25.0 meters, 250. Line over the 0 to show that it's significant. Joules, or 2.50 times 10 to the power of 2 joules. All good. And we could write a little therefore statement to summarize it in context. But I want to move on to the next one. It says, what's the mass of this object? How would you get at the mass of this object? Is there an easy way? If you're told you didn't have to use energy, how would you do it? So 10 times 25 is 250. And this is scientific notation. Yep, just to highlight the sig figs. Yep. How would I figure out the mass of the object? Could I use kinematics? Could I use energy? Could I use dynamics? Look at the stuff that we know. Remember, this is the annoying thing about an exam, is that all the stuff kind of gets thrown at you at once, right? So we still need to be able to know the stuff from previous units. Do I know the force? Do I know the acceleration? Yep.
Yeah, I was going to say, you know the forces that are applied, and do you think all the forces you would find in that force?
Yeah. Look at this. I could say F net is equal to mass times acceleration. That's just Newton's second law. And I happen to know the net force because it looks like that it's the applied force. We're not told anything about friction in this situation. We know the acceleration. We should be able to just rearrange. So F net over m, 10 newtons. Mass, 20, no, what was it? Oh, shucks. I don't even know what I was doing there. I got it conjured up another mass for no reason at all. The acceleration was 4.00 meters per second squared. And so we get 2.50. 2.50 kilograms. And of course, yeah, we could write a therefore statement. You know, I want to throw a part C onto this. What's the velocity after 25.0 meters? You know, we could come at this the same way as we did before. Can you guys see that we could actually just use the equation that we used once before? And we could now use that generalized equation and just plug things in. And that's great. If somebody said, solve this by energy arguments, I would say, absolutely. Let's go back up to that equation that we just derived for sliding objects with work being done on them due to an applied force. Notice that the work this time would be 250 joules, not negative 75. And of course, that would mean that we picked this thing's speed up, right? But if you're not handcuffed in that way, if you're not told that you must use energy arguments, doesn't it just make sense that, hey, if I know 25 meters is the displacement, I know acceleration is 4.00 meters per second squared. If I know V1 is equal to 0 meters per second, and I want to know V2, couldn't I just use a kinematics equation? So in the absence of that, restriction that I must use energy arguments, I can always lean back on kinematics. This is age-old stuff, right? So we can say V2 squared is equal to V1 squared plus 2a delta d. Sub in our values. This guy becomes a 0. 2 times 4 meters per second squared times 25 meters. Don't forget, if I'm finding V2, I got to square root this stuff. 4 times 25 is 100. 100 times 2 is 200. Square root of 200 meters squared per second squared ends up giving us, what do you get? What's the square root of 200? I don't actually know off the top of my head. Obviously, it's the square root of 2 times 10, but 1414? 14.14? Yeah. So approximately 14.14 meters per second. Square root of 2 times, well, it is plus or minus, but the only admissible one is plus. So it's going to be going at approximately 14.1 meters per second to the right. Picks up speed. So we could come at this from a kinematics perspective too. So wrapped up in this question, we got some recall. We've got energy arguments, we've got dynamics arguments, we've got kinematics arguments. And the reason I put this all in one place is that, yeah, we could use energy a lot of the time, but we're allowed to combine all of our previous knowledge now. Okay? And we've got lots of previous knowledge, for goodness sake.